by looking at the sort of minimal set of diagrams and processes that would be active near the transition. Predatory model, and it reproduced, recapitulated the lifetime and puff splitting time dependent on Reynolds number, this super exponential dependence. So today we're going to start off by showing how this simple model makes a prediction for what the universality class of the transition is, and I'll show you the experimental data for that, and then we'll get into the last part, which is looking at the full phase diagram. So you've heard me mention directed percolation. So what is directed percolation? So here is a porous medium, and you're meant to imagine that fluid can flow from site to site along these paths. If there is a link between them, the fluid can go through from one node to the next. If it cannot, then it just stays there. So the way you might think about this is you're making a cup of coffee early in the morning. So you have a filter, you put some coffee grains in, and then what you do is you have a drip and it pours the water on top, and out the bottom comes the coffee. So there's three possible scenarios. So the one is you put the coffee in, you pour the water drips through, and you get your cup of coffee, and it tastes terrible. It's like the sort of coffee you get at a petrol station or something like that, weak and undrinkable. Okay, so then you say, well, that's too bad. Why don't we do something smarter? Let's tamp the grains of coffee together so that they're closer packed. And then the idea is that the water, as it dribbles through the coffee, will take longer to go through, absorb more of the good stuff that makes it taste good. And when it comes out the other end, it'll be great. So you go ahead and do that. You pour the water on. And what happens is it backs up over the funnel, pours all over the counter, and everybody yells at you because you made a big mess, and you didn't get any coffee at the bottom anyway, so it was a complete failure. So of course, what you did was you compressed the coffee grains too much. So then the next thing you do is you say, well, let's just try to get it just right. And if you get it just right, the water trickles through. It takes the longest possible time, contingent on the fact that it actually does get to the other side, and you get a perfect cup of coffee. Okay, so that's what's going on in this processes here. And if you think about all the possible ways that you can imagine this going on, this percolation process, you can see that it's made up, every trajectory is made up of four basic processes. So here in these diagrams, the top line is time now, and then the next line is time t+1. And so what can happen is you can get annihilation where you are filled here, but you just don't get through to the other site. Or you can have decoagulation where you're here, and then stuff flows from here and to here. Or you can have just diffusion, or you can have coagulation as shown over there. And so those are the four basic processes of directed percolation. And so now if you simulate this, so space, we're going to call this direction space, this dimension, which if you think of the coffee percolation is just downwards due to gravity, we'll be thinking of this as the time direction. So P is the percolation probability that you can actually get through to the next site. And so what's happening is if you have P very much larger than some critical value, it's very easy for the percolation to get through to the other side at long time. And so this is the gas station coffee, which is nasty and undrinkable. This one over here, when the probability is too small, the grains are too tightly packed together, so the stuff doesn't get through and just stops. So a long time, you see no occupied sites at long times. So that's the scenario where everything backs up over the counter and everybody yells at you for making a mess. And this one here, there's a critical point where as you just about manage to get through to the other side, meaning that there is some occupancy, site occupancy at long times, and this is the perfect cup of coffee. And this is a second order phase transition and is characterized by by many exponents. For example, this one, we'll call the turbulent fraction, but what it really is the occupation of sites at long times, and that goes like P minus PC to some beta. There's the usual correlation length diverges. Because this is a directed percolation, meaning you always go forward in this time. You can go backwards in any of the other dimensions, but in time dimension, you can only go forward. So that means that this fixed point is unusual. It is an anisotropic fixed point, and that's a particular characteristic of these non-equilibrium systems. Okay, so this is what it looks like. This is a 3 + 1 dimensional percolation. So this is directed percolation. So you start off with a puff. The green are sites that have got turbulence in them above some threshold. The other ones do not. And what's happening is the turbulence is gradually dying away. And so you're watching it, the puff disappear as we talked about. If I took a slice through this and just made a 1 + 1 dimensional picture of what you're seeing there. So here's the time dimension. Here is the initial puff with all the sites occupied. And then gradually it decays away, as you can see in these strands over here. And when the last pixel disappears, there it goes. That is this longest strand over here, just ending like that. Okay, so where do we get this super exponential scaling from that I showed you last time? I don't want to go into a huge amount of detail about that, but one way to see it is this. As I showed you on the previous slide, the lifetime of that turbulent puff is determined by the longest lived of these percolating strands. And in other words, the longest path is a maximum amongst a bunch of independent, randomly percolating paths. So you might think, for example, I take the sites over here, the sites over here, the sites over here, sites over here, and so on. Think of those as being independent random variables. They're percolating through. And now what I'm doing is I'm trying to see what is the probability of having a path, what is the maximum path that I can find. So the longest path is the maximum among these independent randomly percolating paths, and that means that this is a problem in extreme value statistics. So what is extreme value statistics? Well, in the usual statistics that you're used to, think about the central limit theorem. I have a bunch of random variables. They may be IID or they may be somewhat less constrained, but let's say that they're independent, identically distributed for now. So what you do is you say, let me take the sum of those variables or their average. And my question is, if I know what is the probability distribution of those variables, what is the probability distribution of their sum or their average? And the answer, as you know, is the central limit theorem or the Levy-stable distributions more generally. So in extreme value statistics, what you're asking is take a bunch of random variables and now ask not for the mean or the sum, but the maximum of them. And when you work out what is the probability distribution that governs the max, or the min for that matter, what you find is that there are three fixed points. There are three fixed points that correspond to three different categories of source distribution for the underlying variables. Now, the one that concerns us here is what's called a Fisher-Tibbett-Gumbel distribution. So all of these fixed points were developed and derived by Fisher and Tibbett in 1928. They used an argument that is eerily close to a normalization group, and then in one of those distributions, the one that covers most situations is this one here. This is the cumulative distribution, which, as you can see, has this double exponential form. And I'm not going to derive that. Now, what I've told you is a little bit simplistic, because as you're going towards this directed percolation critical point, the correlation length in this direction, this transverse direction, of course, is growing. And so these sites here are no longer independent, randomly percolating paths. But I'm not going to get into that. Okay. Yeah, Freddie. Say it again. Yes. Is there simple? Yeah, there is, but I'm not going to give it now. Yeah. There's very simple ways to derive the extreme value distributions. Can I not spend time doing it if you don't mind? Because I've got a lot to cover. But anyway, these are. If people want, I can show you how to do it. I have a quick way to derive it. Okay. I have a renormalization group way to derive it, believe it or not. All right, now let's talk about the universality class. The basic processes that we talked about last time were predator A and prey B. And here I'm writing down the reactions that I showed you last time, but now I've added labels I and J, which represent lattice sites. Okay, and so so when I say expectation ij, that's not really an expectation. It's really just it means that I and j are nearest neighbor sites. I guess people thought that the angle brackets were underused in statistical mechanics, so they used that notation. So anyway, so these are the various processes that we talked about. Now, a heuristic for how we get to directed percolation. I'm just going to say this is heuristic. It's not the full derivation, as it were. But what we're going to say for this is that the prey population gets very small, and so the predators are not surviving. So what we'll do is we'll just say, okay, let's cross out all the reactions with a predator in them. They will just say that those are negligible. So now I've gone from a 3-trophic level ecosystem to a 2-trophic level ecosystem, where I have the nutrient, which is the laminar flow, the prey, which is the turbulence, and you have these 4 reactions here, which are left. And if I write those reactions down diagrammatically, you can see that each of those reactions corresponds to the 4 basic motifs that underlie directed percolation. So what we've seen from this argument, and it can be made much more precise using functional integration and so on, and I've put in the library of papers that I deposited on Slack, the papers that do this. What we've seen is that near the extinction transition, stochastic predator-prey dynamics reduces to directed percolation. Okay, so is it true? Well, let's have a look. So these are the data from Björn Hoff's group. So these were published back to back in a special issue of Nature Physics devoted to turbulence with our paper and another one. So what they did was they didn't look at a pipe. They looked at Taylor-Coet flow. So that's flow between inner and outer cylinder. This apparatus had a very narrow aspect ratio. So this distance was very small compared with the radius, and this distance here was very small compared with the radius. So it's essentially quasi-one-dimensional, but it's got periodic boundary conditions, which means you can do things with it which you can't do with a pipe. So what you do is you look through a little slit here, you rotate the outer cylinder. That's how you create the shear, that's important. And what happens is it creates turbulent puffs, and those puffs are shown in black here. So what happens is you put a clearoscope into the flow so you can visualize it. You can think of those as being like little fish scales. You fire laser light at them. If the scales are all aligned, meaning in laminar flow, the light comes back to you, so it looks like the bright regions. If the flow is turbulent and randomized, then it doesn't come back, and so you see black. And so what happens as the fluid goes round, you just look through the slit, and you just take a picture as it goes through. One exposure goes through again, another exposure, and so on. And so you get these exposures here: first rotation, second rotation, third rotation, and so on and so forth. And you might say, well, these turbulent patches are pretty much in the same place. But if you take these pictures and stack them up underneath each other, you generate a pattern that looks like this, so that you actually see them moving around. And so what happens is you generate your flow of these puffs, and these are the pictures that you get. So blue is the turbulence, and yellow is the laminar. And for Reynolds numbers less than somewhere around 380 or something like that, you get pictures that look like this. They don't get through to the other side. Above the critical number, the turbulence clearly is present at all times. And at around about the critical Reynolds number, for long times, you see just a little bit of turbulent fraction. And this is more than just a pretty picture. So you can go and then measure the turbulent fraction and fit it. And what you find is that it looks like a power law over about 2 decades of reduced Reynolds number. And the exponent for this is 0.276, which is indeed the predicted exponent for 1 + 1 dimensional directed percolation. That was in 2016. About 6 years later, the same group now did the experiment in 2D. So now this Taylor-Correct system is longer in this direction here. And here are some of their data, the same thing. And the pattern, of course, is much more complicated, as you can see here. It's not just these patches, it's a rather more complicated zigzaggy pattern, which is not yet understood. Okay, that's one of the challenges that we have in the field moving forward. And there the exponents for the turbulent fraction agree with 2 + 1 dimensional directed percolation. Now, it's not just looking at the turbulent fraction. What was done in the papers was looking at things like the separation of puffs, looking at, in particular, this one I particularly like, it's in the supplementary material, doing a quench where you start off with a flow, and then you decrease the Reynolds number and watch how the turbulent fraction decays or goes to a different value, and that is the turbulent fraction is a function of time for different Reynolds numbers, and there's a precise prediction that you can make about how these data should collapse onto a universal curve, and you can see these data do collapse onto the universal curve with no adjustable parameters. The black thing here is the predictions from directed percolation, and these are the known critical exponents of a directed percolation. So this is so there's a lot of data that show that this is working. Just for fun, here is the data I just showed you from the Taylor-Correct experiment. Here is our predator-prey model that I showed you last time. And again, you can do the same thing that you do in the experiments with the predator-prey system with the same outcome. This was also done now in 2 dimensions with a direct numerical simulation by Chantry, Tuckerman, and Barkley. So this is a calculation that was absolutely huge in terms of space and time. I don't really know how they managed to do it. This is a planar shear flow, but it's a planar shear flow with strange boundary conditions on the edge, not no slip boundary conditions, but slip boundary conditions, so that they're essentially able to simulate a system which is effectively at a higher Reynolds number than would otherwise be the case. And anyway, they went and did this beautiful simulation, and again, measured the critical exponents, the universal scaling function, perhaps not quite as nicely as you can do in the experiment, but again, a very compelling evidence to be that it's in the universality class of directed percolation. Question over there. You mean this thing here? Right. So I'm looking at the fluid, and the fluid is being dragged around by the outer plate, and so you wait for the plate to go around once, and so on. That defines the what? It defines this distance here, which is yeah, okay. Okay, so that was that. What was it? Yes. There's also evidence for predator-prey oscillations, although they're not really observable in these pipe or Taylor-Correct experiments because of the geometry. Here is one example, which is motivated by plasma physics. This is a 2-dimensional magnetized electroconvection experiment. I'm not going to go through the details of this. It's basically a 2D electrolyte fluid with little magnets underneath, and you excite turbulence through that. And what happens is you get these sequence of eddies that eventually merge into one large coherent structure there. You can try to write down what the equations for this are, and you expect to see predator-prey oscillations in the Reynolds stress and the energy of the modes, just as we did in the pipe simulations. And then this is the LH mode transition in fusion plasmas and tokamaks. So this is data from Estrada et al. 2012, where they finally observed predator-prey oscillations that had been predicted about 20 years previously by Pat Diamond using mean field heuristic type of arguments. Finally, I want to show you predatory oscillations in thermal convection. So this is a 2D convection. These are simulations done by David Goluskin in his PhD thesis. So this is at Prandtl number 10, Rayleigh number about 2 times 10 to the 5. The boundary conditions here is that you have a cell which is essentially open in this direction. So what you're seeing in this simulation over here is convective plumes rising and falling. Now, as you change the Rayleigh number to crank it up to 10 to the 8, now what you see happening is that you have a zonal flow going this way and this way. This is the turbulence over here, but now the turbulence no longer is able to get to the other side as it does over here because it's being sheared by the zonal flow. And if you go now to keep the Rayleigh number the same and now change the Prandtl number, now what you see happening is bursty shearing convection. So if you watch this movie over here, you can see that it's doing predatory oscillations. So what's happening now is you have a whole bunch of turbulence. Turbulence is exciting the zonal flow. So now you can see the zonal flow advecting the turbulent plumes along like that. Now the turbulence is no longer in the bulk here. And so the zonal flow is going to start to slow down. And then once the zonal flow starts to slow down, the turbulence then re-emerges. And they measured this by looking at the energy in the zonal flow and in the turbulence over here. And you see these predator-prey oscillations. Okay, so what I've told you so far then is for transitional turbulence in a pipe, and in or at least in theoretical models of pipe, and then in these Taylor-Coetz systems, we can see a very strong evidence that this is a non-equilibrium phase transition in the universality class of directed percolation. Okay, so now let's talk about what happens when we go beyond the critical point to higher Reynolds numbers, where we start to see slugs. And this is a work I'm going to talk about now. Shiying Wang, who is on the front row there, a student, worked with me on this, and Hongyan Shi at the Academia Sinica in Taiwan. So this is this paper just came out in Physical Review Letters. All right, so what we talked about so far was a puff decay for Reynolds numbers about 2040. So now what we're going to be talking about higher Reynolds numbers. And now what happens when you go to higher Reynolds numbers is the puff doesn't decay and it doesn't split, as we talked about as well last time. The puff actually just starts to expand and fill the tube. And so what we're going to be interested in now is the propagation of turbulence, the low Reynolds number version of what I talked about in the first lecture. Okay, so let's just recap. So here is a picture from the last lecture where you could see two puffs that have split, and what we concentrated on last lecture was just the dynamics of this simple puff. And but of course we didn't ask the question, like in a real flow, what determines the size of the puff? And the answer is that it's the streamwise shear interactions that determine the size of the puff. So what we need to be asking ourselves is what happens when we start to now include those interactions and not just focus on the dynamics of an isolated puff. So if you include a mean shear, the first person to really think about this in a theoretical way was Dwight Barkley. And what Dwight did was he realized that if I look at the sort of schematic of the turbulence and mean flow that you're seeing in the system, that's very reminiscent of what you see with the voltage spikes in a nerve fiber as a pulse goes down the nerve fiber. So that was something that he worked on a lot. He was an expert in that excitable media. And so he wrote down a nice model based on essentially a sort of generalization of the Fitzhugh-Nagumo equations that really sort of qualitatively captured this very well and was able to make a very nice application of this to the turbulent pipe flow. So I'm not going to talk about this work. I don't have time, but It's very nice, and the papers are in the things that I sent you. The second thing I want to show you is direct numerical simulations by Song et al. Looking at the energy gain and energy loss in a slug. And so this is where we're going to start the story. What I'm going to show you here is that we're talking about a slug. So let me just orient you. All right, so think about the fluid coming in this way. So we'll talk about this as being the upstream front, and this as being the downstream front. And what we're going to be looking at is the energy budget of the system. And so roughly speaking, these are the results from direct numerical simulations of the energy production, energy extracted from the mean flow by turbulent eddies, and this is the energy dissipation in these slugs. Now, I'm going to be using the terminology that I'm going to explain in more detail in a few minutes, but for now, just think of these as being two different Reynolds number regimes, weak and strong slugs, and I'll tell you exactly what is the distinction between them. So basically, what's happening here is in this particular example here in the weak slug, what I want you to think about is the mean kinetic energy is the flow coming in to the pipe. That's the laminar flow, and that energy is then feeding the turbulence that is being generated. And what's happening here is that some of that energy is used to create the upstream front, but what you're going to see is that downstream, the energy production rate is very low. So that's over here in this picture. This is the downstream front, and over here, the energy production is not enough to balance the dissipation, and so you don't have another front downstream. So what these pictures tell you, and this is what you see in simulations, is that what's happening is in a weak slug regime, you're having a strong front at one end and no front at the other. And I'll show you more pictures of that in a minute. Here when you have more energy coming in, a higher Reynolds number, you see that both upstream and downstream, there are two fronts, and they're both pretty much the same as each other. So this picture here, where you see two fronts, that's true in the strong slug regime. In the weak slug regime, this thing just sort of tails off over here. It's not really a front at all. All right, so that's the energy budget picture. So how do we model that using these sort of ecological approaches? So what we do is we draw our picture of the system with the energy described up here. This is the turbulent energy. This is the mean flow energy. And I remember last time I told you about the velocity profile of the flow. So one of the things that you need to know is that the Hagen-Purcell profile was this parabolic form that we talked about last time. Once you have turbulence here, you have a lot of drag, and so this parabolic shape flattens out, and it sort of looks something like sketched over here, and then very far downstream from the puff, that you've lost all memory of where the puff was, and so you go back to the Hagen-Purcell flow. So what's happening is that the mean flow energy drops as you enter the puff, because that energy is being turned into turbulent energy. But then eventually, as you go further and further away, you get back to having a mean flow energy, which is the same as what you had to begin with. And so you have a kind of depletion zone here, which turns out to be important. And that size of that depletion zone is Reynolds number dependent. Okay, so let's ask how we're going to model this. So we now obviously have to model three things. We have to model the turbulence, we have to model the inhibiting factor, the zonal flow, but we also have to model the food source, which is the kinetic energy of the laminar flow. So we introduce a new trophic level, a nutrient, which is the mean flow energy, which we will call N. And so our picture is that this energy is being carried into the pipe by mean flow as shown over here. So here's the energy coming in. So this is energy in little particles hopping around on our lattice like this. And then the next thing is you enter the this front over here. So the turbulence gets energy from this mean flow, and that slows down the mean flow, and so you have lower energy over here. And so what's happening is now the turbulence is now generating more and more turbulence, and so you have pre-birth as a result of the energy extracted from the mean flow. Then as you go further downstream, this Hagen-Purcell profile slowly recovers behind the turbulence like so, which basically just means that the kinetic energy is now no longer being slowed down by the turbulence, and so it is essentially growing. It's green here to remind you of grass. Okay, so it's literally just growing. So when we write down the equations for the system, we have the same equations that we've had before, but now we also have these interactions between the nutrient hopping to the right, the nutrient growing, and the nutrient feeding the prey. This is the way that we minimally model the interaction between these levels of description. So here again are the full equations. These are the new equations that describe the third trophic level. And now with this in place, we should be able to simulate, recapitulate the full 3D behavior. So let's see how it works. So the first thing is I want to point this out. The nutrient recovery is a function of Reynolds number, and we can work out how that scales with the Reynolds number just by looking at the initial value problem of fluid in a cylindrical geometry. It's easy to solve that, and you can see that the energy grows like u squared, of course, and so the growth rate, this parameter here, should scale with the Reynolds number squared. Okay, so here let me show you some results. So this is these are world lines. So again, this is space, this is time. We are plotting on these colors here the turbulent intensity, and here we've got a readout showing you the nutrient and prey density over here. So what's happening in this picture here is you have a localized puff that is moving backwards in the laboratory frame, as we talked about last time, and it's just a puff just sitting there like that and just moving backwards. This is what you see in direct numerical simulations and experiment. As you go now to a higher Reynolds number, the puffs split as we described last time, but now we can describe that splitting event much more faithfully, because what we were looking at last time was just when does a patch of turbulence go unstable and start to split through some sort of pattern-forming instability. We weren't interested in trying to understand what happens to the puffs thereafter and look at the puff interactions. But now this model can actually do that. And so you can see here, this is the world lines that arise from the puff splitting. And these are the data from the Hoff Group's 2011 experiments and simulations. So if we now go to higher Reynolds numbers still, and we look at the slugs, so this is a picture of a slug. This is a weak slug. So this is a regime where the fluid is coming in from the left. It's causing a turbulent front over here on the left, but that energy is all eaten up by this front here, and there's very little left to form a front on this side over here. So the energy just simply decays. The turbulent energy just sort of decays to zero as you go through this weak slug. And these again are data from experiment over here, from this paper from Dwight Barclay and Björn Hoff. And again, you can see the cross-stream velocity fluctuations starting off peaked at this front here, and then gradually dying through the middle of the puff. As you go to higher Reynolds numbers still, now you have, the way I want you to think about it is that you have enough energy after this front has been formed here that you keep the turbulence alive here and can even support a second boundary, a second front on the downstream side, and that's shown over here with the turbulence intensity as measured by density of prey. And then these are the experimental data for the velocity fluctuations, showing you have this symmetrical, strong slug. So, and then more quantitatively, if you look at the front speed, the upstream and downstream fronts as a function of speed, these are experiments. The blue, these are experiments by Hoff. The blue here are simulations that are done using the excitable medium model, and over here is what you get from the predator-prey model. What I want you to notice is the asymmetry here. You can see the downstream front and upstream front behave in a similar way at high enough Reynolds number, and then at lower Reynolds number, you can see that there is this asymmetry in the upstream and downstream fronts, as you can see with this upward curvature here and here. So what is the role of stochasticity in all of this? Well, the stochasticity comes in a lot of ways. I'm not going to talk about all of them. I do want to talk about the puff splitting, and somebody had asked about that at the beginning. So we're talking now about this range of Reynolds number. This is the turbulence density of prey intensity. This is the kinetic energy of the mean flow. And the point is that there's a very high turbulence decay probability in this red shaded region because there is very little turbulence production because there's little kinetic energy from the mean flow. So you might ask, well, is it possible that there could be a fluctuation that would enable a puff to form as I go downstream? And certainly, if there is some turbulence that somehow manages to survive from here, manages to sort of, as it were, tunnel through this pink region, once it gets to here, then it will start to be fed by the kinetic energy of the mean flow. And so then what can happen is any puff, any bit of turbulence that survives over here will be the seed and nucleus of another localized puff, which can then grow. And what's going to happen is the kinetic energy goes as u squared, whilst the advection speed of the turbulence patches scales like u. So what's going to happen is a daughter puff is going to start off over here. It's going to travel initially slower than the mother puff, and then eventually will start to move at the same speed and start to move parallel to that. And that's what you see in the experiments and what you see in this model. Okay, so I want to talk about the propagating fonts here. So I want to just, what I want to explain to you is the role of stochasticity. So this is what happens if I take the mean field equations for these fronts, which I'm going to explain a bit about those in a few minutes, where they come from. And then this is what happens when you look at the full stochastic simulation. And I want to just walk you through the phenomenology of this, and I'm going to go to the blackboard and show you how we work this out mathematically. So over here, you have a sharp front, as you can see, in this weak slug regime. And here you have what we call a weak front, basically where there isn't enough turbulence intensity to support an actual front. Now, this front, and I'm going to explain what this means in a few minutes, this front is a particular kind of traveling wave. And you may ask yourself, well, we already talked about the propagation of turbulence in the first lecture. Isn't it going to just be like that? Well, the answer is no, it's not. Because what we talked about in the first lecture was high Reynolds number, and we used K41 scaling to be able to estimate the form of the equation. And what we saw was that we had a nonlinear diffusion equation where the nonlinearity occurred inside the del squared term. And that came from the K41 scaling. That came from the cascade. Here, at small Reynolds numbers, but still turbulent, we have hardly any cascade to talk about. So it's absolutely not correct to be talking about K41. So one has to ask in what places that. And I'm going to show you that what you have is a kind of front known as a Kolmogorov, Petrovsky, Piskunov, Fischer front. And I'm going to explain what that is in a few minutes. And the punchline of what I'm going to show you is that this kind of front is actually a bistable front, exactly as you would get in an excitable medium. So one second. Oops. Go away. What is this thing? Wait, what? Okay. All right. So now down here at this weak front, there is, as I've said, there's not enough energy to support a front, and so you get this weak front like this. I'm not going to talk about the stochastic Lie effect, although it's super interesting. Okay, I'll take a question and I'll move on. Ulysses, Sebastian, then you. Okay. Yep. No. So the question is there a connection between the mean flow and the zonal flow? So the zonal flow becomes less important once you get away from the critical point, but the stochasticity that arises from that is still important in controlling the profile that you see. I'm not going to have time to go into that in detail, but it's not the same thing as the mean flow that's coming in. So just like you heard from Steve this morning, and as I mentioned last time, once you have these turbulent flows, they can create emergent mean flows that then interact back on the flow that you already have. So that flow is essentially orthogonal to the mean flow. Now, there may be some small interaction with it, and there's certainly, you know, if you're trying to think about, say, streaks, streamwise streaks and things like this, you might think that there could be some such coupling. I'm certainly not going to rule that out, but it's not a part of this model, and it's not needed for this description. Okay, somebody else has a question. Yes, you did. Yes, the stochastic model breaks the symmetry. So the reason is this. Okay, so why don't you have the weak slug in this regime, right? So the reason is this. So in a stochastic model, I literally take into account the quantum of energy, the food. So all the energy got eaten by this, and there's none left over here. In mean field theory, you just average everything and divide by 2. That's why. Mean field theory is not, just in the same way that mean field theory is not adequate to describe predator-prey oscillations. You need to go to the next order in fluctuations. So the same thing is true here. So let me go on to those fluctuations. So these are the stochastic equations for this model. You can then go ahead and work out the Van Kampen expansion, work out the equations for the number densities of predator, prey, and a nutrient. And these are the types of equations that you get to mean field order, not including the stochasticity. So these equations are a generalization of the KPP equations. I'm going to describe that for you in a minute. So this is what the Kolmogorov, Petrovsky, Piskunov, Fischer equations are. It's an equation that looks like this. It's a reaction diffusion equation. So there's a d rho by dt, there's a diffusion, there's a growth and death, and there's competition. And this equation is a generic equation for many different processes: spread of genes, combustion, all sorts of things like this. But the most important thing I want you to understand is that this equation is an equation that describes a front that interpolates between a stable state that is invading an unstable state. And so you've got a thing that looks like this, and this is moving to the right. And that's the process, the invasion process that we want to understand. Now you might say, well, this is just some wave moving along like that. What's the big deal? Why are big names like Kolmogorov and Fischer and so on wasting their time on this? Well, you'll see it's really fantastic. What happens in this equation is very, very, very surprising and was very unexpected. Now, that's the KPP Fischer equation. Here's the equations of directed percolation that you've seen before, making these pictures here. If you look at this equation here, it has a front that propagates in time and space. So you can see that will look in space and time something like this. This is the front moving at some fixed speed. If I look at the directed percolation pictures, let's go to this regime where you can see it more clearly. You can see again, you've got this spreading process going like that. And so you might say, oh yes, it's fairly obvious that this kind of spreading process in space-time would be described by an equation like this. And in fact, it's not just an analogy. If you take this set of stochastic reactions, write it down as a Martin-Singer-Rose field theory, and write down the corresponding Langevin equation, and what you get is this equation here. By the way, this square root is a mistake, so it's a typo, so ignore that. But this what you get is this is the mean field equation plus stochastic noise, and this noise, I want you to notice, I'll mention it again later, is a multiplicative. The noise involves the field that is the density here. Okay, so I think with that, I'm going to go to the blackboard. So what I want to show you now is a mathematical description of these fronts. I'm going to show you that it's very different from what we did in the first lecture. And we're going to see that these fronts interpolate between a stable state invading an unstable state. But then you might say, wait a minute, we have an absorbing state here. So we have an excitable medium in some sense. So you would think that the fronts would be stable states invading a metastable state, in other words, a bistable front, rather than stable states invading an unstable state. And how this happens, how you go from this naive picture to actually what is really going on is absolutely incredible. And the way it works is resolved by the normalization group and structural stability. And I'm going to show you, I'm going to show you that explicitly, but not in too much gory detail. Okay, so let's start off then with section 4. So this is going to be KPP Fisher fronts, like so. And so let's write down the actual equation. So here is the equation written down as I've written it on the blackboard, on the slides. Like so. So the important thing is that psi is meant to be some non-negative density. So it has to be non-negative like that. P minus PC is positive like so. And I'm going to, for what I'm going to do now, is I'm just going to say that scale this into units, and we'll set this thing equal to 1. So we can put that back later on. And then what my boundary conditions are is that at minus infinity, I want psi to be plus 1. And at plus infinity, I want psi to equal 0 like this. So I have the picture that I've shown you before. So here is space. Here is psi, here is 0, here is 1, and then I have a front that is propagating, like so. It's going like this. It has some speed, c, and this point here, psi equals 1 is a uniform stable state, and psi equals 0 is a uniform unstable state. Linearly unstable. So that's something that you can check if you want to, if you're bored with 3 weeks of lectures and you want to do some calculations, you can check by linear stability these things like so. Yes, the density, exactly. Okay, so what you can do is just do linear stability analysis and check that psi equals 0 state is linearly unstable, the psi equals 1 state is stable. Okay, so all right, so now let's look at the steady states of this equation, and I can do this up here. So I'm going to write down the equation the following way. So I'm going to write it as d psi by dt is minus df deep psi, where this the Appler functional is 1/2 deep psi dx squared plus some potential of v of psi integrated dx, like so. And v of psi we can just read off as minus 1/2 psi squared plus 1/3 psi cubed. So basically what this looks like is the following. Here is psi, here is the potential, here is 1, and now what I've got is a curve that looks something like this. Now, what we're interested in understanding is the presence of traveling waves, a special kind of similarity solution. So what we're going to seek is that psi of x and t is of the form psi of x minus ct and t. So we're going to look for a solution like that. And then what we're going to actually be interested in is the long time limit. So we just get psi goes to x minus ct without the t, and that's going to be true in the steady state in the co-moving frame. So that's what we're looking for. So in order to do this, like you do with any similarity transformation, what you do is you define a new variable, which I'll call z, which is x minus ct, and then I'm going to transform this equation into these new variables. So if I do that, then what I get is d2 psi by dz squared plus c psi by dz is equal to minus psi minus psi squared. And I'm going to write what's on the right-hand side here as minus du by d psi. So u is a new potential. So this u is equal to 1/2 psi squared minus 1/3 psi cubed. And so this is actually just the inverse of the original potential for the KPP-Fisher equation. So if I were to plot that, what I would get is this. So here is psi, here is this potential for the steady state equation. And then what I have is an inverted potential. So that inverted potential looks like this. And here is psi is 1, here is psi of 0. And then the other thing that we have to remember is that psi always has to be non-negative. So this region here is unphysical. So it can't go over there. Okay, so that's the steady state equation for our system. So let's think what this means. Well, if you think about it, this is like Newton's equation for a particle moving in a potential u. So if I were to write that down, I would say d2x by dt squared plus maybe some viscous damping is equal to minus du by d psi. So this is Newton's second law. So I can see then that there's an analogy here. That analogy is that psi is like the variable x, and z is like the variable t, and c is like the variable eta. So the speed in the KPP-Fisher equation is the speed of the wave, the thing that we're trying to calculate, is like the viscous damping dissipation in this mechanical analog like this. So what we can ask then is, well, what is the thing that we're trying to understand? Well, any trajectory that corresponds to the solution of this equation, what it corresponds to is a particle that starts off here at psi equals 1, goes downhill like this, and at t equals infinity, eventually gets to the origin, but doesn't overshoot. And that trajectory in x and t is the trajectory of the shape of the front in psi and z. Okay, so that's the problem that we have to solve. Well, that's easy. You learned how to solve this on your mother's knee. This is just damped motion in a potential using classical mechanics. So what's going to happen is very simple to understand, because what we understand then is the answer to our question, what is C? The answer is that C has to be greater than or equal to the critical damping in this potential U of psi. So you can work that out. You can work out the critical damping, and in these units, it's equal to 2. So basically, as long as C is greater than or equal to 2, which is what I'll call the critical speed C star, there exists a stable, it turns out to be stable, steady state front. Okay, so that's great, except it's not what happens in real life when you do an experiment or when you do a computer simulation. So let's find out what happens when you do a simulation. So what you do in a simulation is you start off at t equals 0 with a shape, let's say like this, psi as a function of z. You start off with a shape that might be, say, a step function, or maybe a Fermi function, something like that. So you set this off at time t equals 0, and then you evolve it in time to get a propagating speed, a propagating front. And then what you find is that the propagating front that you have looks just like what we expect, and it moves at a speed c is equal to c star, which is equal to 2. And so you say, oh, fine, well, maybe something went wrong there. So you change your initial condition, you do something like this, you wait long enough, it always goes to speed c equals 2. Unless the front decays so slowly at infinity, like a power law, then you can get a higher speed. So this is what the initial value problem gives you. Unique speed for a front that is a global attractor. And the steady state equation gives you a family of fronts. And so you have a problem. How do you resolve this question of how can I tell from just doing the steady state analysis that there should be a front that is actually going at speed c equals 2 rather than just any arbitrary speed? So let's solve that. So this is a problem that has been of interest since the 1930s. And indeed, what KPP and Fisher were doing was they were trying to figure out the answer to this question. They already could do the analysis that I've just done for you, and they try to understand what is going on there. This problem was finally resolved mathematically by Aronson and Weinberger in 1975. But people still wanted to understand physically what's going on. And the way that we understood this in the middle 90s was using renormalization group and structural stability. So this is a very cool way to see what is going on. So this problem is called velocity selection. I do the steady state analysis, I get a family of solutions. I do the initial value problem, I get one solution. How do I choose? How do I select which of the steady state solutions is the one that is selected by the initial value problem? Now, the insight that we had on this was that, what is special about the selected solution? And people tried various answers to that, such as marginal stability and other things like this. Our idea, because we thought about this from a renormalization group perspective, our idea is that the long-time solution to the initial value problem is the member of the family of solutions that is structurally stable. Now, we've talked about linear stability in these lectures, but we haven't mentioned structural stability. So what is structural stability? Structural stability is the idea that if I have an equation or a model of some physical phenomenon, and I make a perturbation to that model of order epsilon, the change to the predictions of the model should also be of order epsilon. So the idea is that I can think of a governing equation in a space of equations like so. And then I can think of the solutions to that equation, to that model, for some physical phenomenon. And what I should have is, of course, no model is perfect. So I can write down in various models for some particular process, and they all form some epsilon ball in this model space. And then I should be able to make a prediction from each of these models. So here's the predictions. And they should also form a set of predictions that are also of order epsilon in the solution space. On the other hand, so if that happens, that's called structurally stable. But if, on the other hand, what happens is that your solution space, what you get are solutions that look like this. So this map from here to here now is huge. So the variance here is not of order epsilon, but is of order unity. That's called structurally unstable. So what we want in physics, of course, is that solutions to models should be like structurally stable. In other words, we expect that in order to be able to do physics, you need to have structurally stable predictions. And there's a renormalization group way of thinking about that, which is in our paper and puts it on a precise mathematical formulation. I'm going to show you qualitatively how one can understand what's going on here. So let's apply this. KPV Fisher problem. So what we're going to do is we're going to imagine that we've changed the equation itself. So here is the essential part of our equation. We have diffusion in a potential that we already calculated looks something like this, and the particle is sitting at the top and is eventually going to roll down to the origin. Now I'm going to show you a perturbation that we can make to the governing equation, not a perturbation to the solution like we do in the stability analysis. And what we're going to do is we're going to make a perturbation over here, and then the solution is going to go up like this. And this perturbation is of size epsilon. Okay, so what do you think is going to happen? Well, say it again. I'm changing remember the equation is d psi by dt, del squared psi plus u of psi, and now I'm adding a perturbation to this, which I can think of as a perturbation to this potential. So the perturbation I'm going to choose is the one shown over here. So now let's think what happens. If I ask for my particle that is going to make its way starting from here, going down to here, what you can see is that the particle that goes down here, gets all the way up this hill, just gets to the top here, and then stops, doesn't violate the boundary condition here. The speed for that selected particle is going to be 2 minus something of order epsilon. Well, now let's have a look at what happens when the speed, meaning the friction, is greater than c star. Now what's going to happen is the particle is going to go down here, but it's got too much friction. So it's going to go up here, get, say, up to here, and then start oscillating around this well, and it's never going to get to the origin. So all of those solutions with c greater than c star will never satisfy the boundary conditions. So I've made an order epsilon change to the equation, and I've made a huge change to the solution spectrum. Most of the solutions got wiped out, except for one. And that one solution is the selected solution. So what have we learned? What we've learned is when we look at this front here, when we look at what the selected solution, what we can see is that the selected solution PPT Fisher is the limit of a sequence of bistable fronts. Because these fronts here, it goes from a stable state to another locally stable state. Whereas over here, it's stable. Over here, it's unstable. So the selected front, the speed that it actually observed, is the limit of a selected front that is the limit of a sequence of bistable fronts. And that's the solution to the velocity selection problem. And it is also why the fronts that occur at these low Reynolds number slugs are indeed similar to the ones that you would get in an excitable media. They're not, there's a particular speed at which they move. Okay, so I'm going to go back to the lecture. So that's where those fronts come from. I want to now just finish by talking about quasi 1D in the Taylor-Coët system. So what I've just shown you is why you get these sharp fronts, why they move at a particular speed, and how that description comes out of the mean field behavior of the directed percolation type of pictures. Okay, now what we can do with this type of model is we can look at different types of flow geometry. So I've been talking up to now about pipe, where the flow is pressure driven. But I showed you the data from Björn Hoff, where the data are in this Taylor-Correct system, where it is shear driven. And the shear is driven by this outer cylinder that is rotating like that, putting energy into the system. So what's happening is that the direction of energy flow is different. Now the direction is not just coming in from the left, it's seeding it like so. And so what that means is that the mathematical description in terms of this stochastic model is now that this is happening globally as opposed to locally as it was in the pipe system. So when you run the simulation in that geometry of energy flow, what happens is you no longer get this energy depletion zone, you just get a uniform energy in this region. And so when you now simulate that and make the pictures, you can see that they look like what you see in the experiment. There's no drift and there's no depletion zone. Okay, so what I've told you then is that in the transitional turbulence regime, now we've talked about puffs, we've talked about puff splitting, we've talked about weak and strong slugs. All of these different pictures all agree with what you see in the experiments. And that is my summary for this part. So I will leave it like this and we can have some questions. And actually, if anybody wants to ask me about the laminar turbulence transition as a symmetry breaking transition, I have some Blackboard notes on that as well, with the punchline being that this is a transition between a PT symmetric state and a PT non-symmetric state. But anyway, I'll take some questions.
The phenomenological point model, predatory model.
Yeah.
But I'm wondering, how do you like to reconcile it with the Navier-Stokes equation, which is more from first principle?
Yeah.
What's your idea about how to link between the phenomenological model and the Navier-Stokes equation?
Okay, so the question is, how do you connect these sorts of phenomenological models with the Navier-Stokes equations? So the first thing is, as I told you in lecture number 2, even for regular phase transitions, like the Ising model, we cannot go from the microscopic equations to the macroscopic phenomenological description. Okay, we cannot do that. You cannot go from the microscopic physics of electrons in a magnet to writing down the Ising model. Okay, every approximation that you make there is not systematic and is not valid. Okay, you can make them and wave your hand, and then you later justify it by renormalization. So as I said at the time, when you start making these models for the laminar turbulence transition, you should not expect to be able to derive it from microscopic equations with a series of operations that are systematic, and then everybody's happy. It's not just like doing some Taylor series expansion of something. Okay, everything here that I've told you is exploiting renormalization group ideas of universality and so on. So you cannot understand it without understanding it from a renormalization group perspective. Okay, so that being said, in the papers I put in on Slack, there's a paper I wrote in 2017 where we worked out the mean field derivation of the predator-prey equations. Okay, now you can say, well, there you are, there's the answer to my question. Well, remember what I told you? It's not systematic. You cannot justify any of the approximations, because any mean field approximation breaks down in the vicinity of the critical point. Okay, so you have to understand these things as you make the phenomenological model, then you use renormalization group ideas of relevance and irrelevance and so on to show that this is the right description. I didn't have time to show you that, but we can do that for these models too. Not the ones I've shown you so much here, but other models of interacting puffs and so on. That's in a paper that we haven't yet submitted for publication. And I didn't have time to tell you about that. So phenomenology is not a dirty word. Okay, I mean, what I like to tell my students is this. I'm sure you remember from taking my StatMech class. I do a derivation of Navier-Stokes from diagrammatic perturbation theory and Boltzmann equation. And it takes me a couple of black holes. Then I derive it in 2 or 3 lines phenomenologically. Okay. Then I ask the students, which one do you prefer? And of course, they all prefer the one with perturbation theory and blah, blah, blah. And then I point out to them, well, wait, when I have your Stokes equations, do you think they apply to a dense liquid? They do, right? But does the Boltzmann equation apply to a dense liquid? No. So that derivation that seems systematic is restricted to the domain of validity of perturbation theory. But the phenomenon is much broader than that. So these phenomenological derivations that capture the essence of what's going on, minimal models as we like to call them, they're not, that's all you have when you can't do systematic perturbations with a small parameter. And so you have to use that plus the normalization group ideas in order to justify the models. So did I answer your question?
Yeah, I was thinking more about that, but I think that's a good question.
Yeah, if you figure out a way to solve it, to write all this down from first principles, I'll be very happy to hear it. And certainly you can, you know.
Direct numerical relation to fluid show a row of.
Yeah,
maybe say, oh, there's my separation.
So we well, I mean, I don't know why I want to do that, but what I haven't shown you is, for example, using this stochastic model. So there's lots of measures of the energy budget that I didn't show you. Okay, and so we've measured all of those things, and they're in a paper that we're just finishing for publication as well. And so everything that you saw in the direct numerical simulations by the Song et al. Paper from 2017, we replicate that in the stochastic model. We don't have to put it in. I mean, they're just solving Navier-Stokes. We're solving this model. It replicates all of that phenomenology. And if you want to ask, well, what scale does it replicate it at, or so on, well, yeah, somebody else can do that. Okay, Brad. Yeah. Thanks for that good comment. But it's exactly as Steve was saying this morning, and Brad was just saying. You know, when Steve was writing down the diagrammatic expansion for the quasi-linear, and then there was what was the term? The pain in the neck term, which you just set equal to 0. Okay, there's no justification for that. I mean, it's knowingly doing that. It's just the sort of closure approximation you're forced to make, which cannot be justified in this range that we're in this regime that we're talking about here. That's the whole point about why critical phenomena are so hard. Okay, another question. Yeah.
I guess for me that seems surprising that in all these slightly different versions of Navier-Stokes, essentially that you get the same thing. I was wondering if that's an obvious thing to see from Navier-Stokes.
No, I don't. No, you're not missing anything. I don't think it's obvious. I mean, when people found these things, it was a surprise. And you know, in the MHD literature, I mean, I'm not an expert in MHD, but you know, what I understand is, you know, Pat Diamond proposed these things, you know, very heuristically. You can't justify it, like in the middle 1990s, and it really wasn't until 2011 that those things, the reality of these modes, was seen in the LH transition in Tokamak in Spain. So it's not obvious how to see these things, and I don't have a simple explanation of why there should always genetically be these sort of activator inhibitor type of dynamics that's regulating turbulence. But I think it's very natural that there should be something that's doing it, and like most things which are subcritical, then there should be something that's activating and something that is inhibiting. And so that's the way you have to think about it. And we use the ecological interpretation of that as a way to motivate, where is the energy flowing in the system, and trying to make these stochastic models of the energy budget. Thanks, yeah. Yep. No. No, not u equals 0. Some non-zero u, but we're not trying to predict is the critical point at 2038 or something like that. Okay, we're not trying to because the whole point of when you're doing, say, writing down Landau-Ginzburg theory for a phase transition, TC is a parameter you put in. You can't derive that from that level of description, and it's not universal. What is universal is the phenomena in deviations from critical temperature. What's universal here is universal in deviations from the critical temperature. So these sort of phenomenology plus renormalization group ways of modeling nature are designed to answer certain questions, but not other questions where you need to know all the microscopic details. No, and I couldn't care less about it. Okay, no. The only reason I might care is that there's that the flow of fluid in your blood, in your heart, when your heart is pumping at the maximum, is about Reynolds number 2000, and so that transition to turbulence that can happen causes stress on the walls of your arteries and can give you aneurysms, and it does. So I was giving a lecture like this, and there were some biomedical people in the room, and they said, this explains why 2000 is this terrible number. So it has health implications. But other than that, I'm as a statistical physicist, I'm not that interested in knowing the precise critical Reynolds number for a particular flow. And I mean, Björn is interested because he wants to measure it accurately and so on. But so that we can then measure the deviations from that and measure critical exponents and scaling functions and so on. But the actual number is not something that has any specific significance, whether it's 2038 in the pipe flow or 357 in Taylor-Coët or something else in another geometry. It's just a number. Steve. Can't hear you, Steve. Yes, yeah. I'm not sure. I mean, we did this in a Fizrev letter in the 1990s, and yeah, I mean, these are strange problems where you have these velocity selections. The question I thought you were going to ask is there a version of this for pattern selection? Okay, which is the spatial version of this. In other words, I can have a, as you well know, you can have some particular, control parameter above threshold. You'll have a range of wave numbers of, say, a periodic pattern, like you would have in, say, convection. And you might say, well, which is the one that's going to be selected by a particular kind of initial condition? People have done those experiments, and certainly it's known that there are certain selected wave numbers. And I think this kind of mechanism probably would apply to that too, but I've never applied to it. That's correct. That's correct. Yes. This is just like Andronov-Pontryagin structural stability, but used in a here we've weaponized it, right? We've used it to actually as a principle for identifying solutions from just taking steady state solutions and trying to say save you solving the initial value problem. Look at the solution, see which one is the one that works. And everything I showed you here was cartoon-like, but in our paper we worked out, mathematically what class of perturbations are allowed, which ones are physically small, but mathematically have a large effect. Yeah. Yeah. The predator is in the model, yes. Yes, yeah, yeah. That's what I showed you last time. Yeah, that's how we discovered it. Yep. Yes, yeah. Wait. What? So what was the question again? Oh, right. So correct me if I've misunderstood the question. So last time I talked about regular perturbations and singular perturbations, right? And I gave us an example of singular perturbations where there's a small parameter multiplying the highest derivative of, say, a differential equation. So if you set epsilon equal to 0, you would have lost, the order of the differential equation would have changed. You need less boundary conditions to specify it, for example. So the epsilon equals 0 case is different from the case where epsilon is non-zero but asymptotically tending towards 0. Is that the thing you're thinking? Oh, okay. I know what you're asking. I think you're talking about there's a even if I have, so there's a certain threshold that a perturbation to the flow has to be above in order to cause you to create the transition. That's the thing, and I mentioned that even in cases like Heisenberg's PhD thesis on plane Poisson flow, where there is a point where where it becomes linearly unstable at Reynolds number 5,700 or something, the transition actually occurs much before then, because the amplitude is small enough compared to the ambient perturbations that the system just jumps from the stable state to the turbulent state. Yeah, what is it? Nobody really knows. I mean, I think it depends on what is the actual pathway to go from the stable state to the state that represents the unstable state. So it's a kind of, the way I want you to think about it is it's like a nucleation problem. So it's like some instanton trajectory that goes from one to the other, and at some point that instanton, you've got enough noise or background perturbations that you've got a finite probability of being kicked over a potential barrier into the next basin of attraction. And so it's not universal. The process by which it happens might be universal, but what the actual amplitude is not. And so just like in the pipe flow example, if you're Bjornhof and you do the experiment carefully, you can say that the transition occurs at this 2040, but 2038. But if you do an experiment where you just try to reduce the background noise, you can try to keep the laminar absolutely linearly stable state stable to Reynolds numbers up to 100,000. But then if somebody in the room sneezes, then it'll become turbulent. So did I answer your question? Yep. Okay. If not, please ask me afterwards. Okay.